All right, let's get right into it. We're going to talk about something you probably use every single day if you write Python, the dictionary. You know, it's the workhorse of the language, it's fast, it's flexible, and we all just trust it. But what if I told you that its most famous feature, that lightning-fast performance, is kind of built on a lie? A very convenient lie, but a lie nonetheless.
So just think about it for a second. If you're in a coding interview or you're just talking shop with another developer, what's the one thing, the one fact everyone knows about Python dictionaries? It's that lookups are fast, like really fast. We say they are constant time.
And of course, here's the chart to prove it. We've all seen this table, right? Getting an item, adding an item, deleting one. The average case is O of 1. Constant time. It shouldn't matter if your dictionary has 10 items or 10 million items. In theory, the lookup takes the same tiny amount of time. It's basically magic.
But that's just not the whole story. It's not even close. And the first clue is right there on the slide. In that column nobody likes to talk about, the amortized worst case. That little O of n you see? Well, that hints at a much darker, much more interesting reality hiding just under the hood. So let's go find those cracks in the foundation. And it all starts with two big ideas that every dictionary has to wrestle with: collisions and resizing. See, deep down, a Python dictionary is just a hash table. The concept is actually pretty simple. You take your key, you run it through a special hash function, which spits out a number, and then you use that number as the address, or the index, to store your value in a big list. It's like a perfect filing cabinet where you instantly know exactly which drawer every single file is in. But here's the problem. What happens when the hash function gives you the same index for two totally different keys? That's called a hash collision. And all of a sudden, your perfect filing system has a problem. Two different files are trying to go into the same drawer. Now what do? Our instant lookup just hit a snag.
Now, there are a couple of ways to handle this. One is called chained hashing, where each drawer in our cabinet just becomes a little list of all the files that belong there. The other way is called open addressing, and this one's simple. If the drawer is full, you just look for the next empty one down the line. That process of looking for an empty spot is called probing, and that's the one Python uses. Remember that.
Okay, so you can probably see where this is going. If your hash table gets too full, you're going to spend a lot of time just probing around looking for empty slots. We have a name for this fullness. It's called the load factor. And to keep things running fast, Python is constantly trying to keep that load factor low. It never wants the dictionary to be more than about 2/3 full.
So what happens when you try to add one more item, and that item would push the load factor over that 2/3 limit? Well, the dictionary has to get bigger. It has to create a brand new, larger table and then painstakingly reinsert every single item from the old table into the new one. This whole process is called resizing. And right here, this is the moment our whole O1 story just falls apart. That one single insertion that triggers a resize is not a constant time operation. It is an ON operation. Its cost is directly proportional to how many items are already in the dictionary. Suddenly, adding one tiny little thing to your dictionary can become an incredibly expensive operation. So how on earth do we get away with saying O of 1? Well, it's through this clever bit of, let's call it creative accounting, known in the biz as amortized analysis. The argument goes like this. Yeah, those ON resizes are super expensive, but they're also really rare. Most of the time, your inserts are super cheap. So if you take that one huge cost and spread it out, or average it over all the many cheap insertions that came before it, the amortized cost for any single operation looks like O of 1. It's a useful idea, but it's an average, not a guarantee.
Okay, so that's the big picture theory. But the way CPython actually implements this is, frankly, brilliant. It has some really clever tricks to make this all as fast and efficient as possible.
Since Python 3.6, the dictionary uses something called a compact layout. So instead of having one huge table with a ton of empty space in it, it splits the job in two. There's one small, sparse array that just holds the indices, and then a second, tightly packed array that holds all the actual data, the hash, the key, and the value. It's a super smart design that saves a ton of memory, which also means it's more likely to fit in your CPU's cache, making everything even faster.
Now here is where it gets really wild. You would assume that Python uses some incredibly complex, super random hash function to avoid collisions, right? Nope. Turns out, as this comment from the actual CPython source code admits, it doesn't. For integers, the hash of an integer is just the integer itself. This is amazing for the common case where your keys are 0, 1, 2, 3 because you get 0 collisions, but it also creates a massive, predictable vulnerability. So to deal with this ridiculously simple hash function, CPython uses an incredibly clever probing formula. When a collision happens, it doesn't just check the next slot over. No, it uses this formula to jump around the table in a very complex pseudo-random sequence. And the secret sauce is that perturb value. It's made from the higher bits of the original hash, and it completely scrambles the probing sequence. It means that even if a bunch of keys land on the same initial spot, they'll all take completely different paths to find their home.
So we have this amazing system. It's fast, it's memory efficient, it's robust, it's beautiful. But what happens when someone studies this beautiful system, not to admire it, but to break it? This is where the theoretical worst-case scenario becomes a very real, very catastrophic failure. This quote comes from a discussion about competitive programming, where it's actually part of the game to try and break other people's code by feeding it the worst possible input. This kind of thing is called a hash flooding attack, and it's a form of denial of service. And it turns out, because of that simple integer hash, Python dictionaries were a perfect target.
So here's how the attack works. A clever attacker realizes they don't even need to find keys that have the same hash. Instead, they can reverse engineer that probing formula. They can craft a very specific set of integer keys that are guaranteed to collide with each other, one after the other, creating this long, ugly chain of probes. They are literally forcing the dictionary into its absolute worst-case behavior, turning every lookup into a long, painful walk down the table.
And the result? It's just devastating. I mean, look at this. This data is from the actual bug report. A normal lookup for a key that isn't in the dictionary is basically instant. But looking for one of the attacker's special keys in that exact same dictionary took 5 full seconds. Let that sink in. That isn't a small slowdown. That is 5,000 times slower. An operation that we all count on to be one of the fastest things in Python has just been weaponized to completely freeze a program.
So, let's pull this all together. What is the real, honest-to-goodness truth about O1 when it comes to Python dictionaries?
Well, here are the crucial takeaways. O1 is an amortized average case. It is not and never has been a constant time guarantee. It relies on a few key assumptions, that your hash function is doing a good job spreading things out, and most importantly, that the data you're getting isn't actively malicious. The worst case for lookups, inserts, and deletes is and always was ON. Now, for 99.9% of what we do, dictionaries are going to be blazingly fast. But as engineers, it's our job to know about and plan for that other 0.1%.
I'm going to leave you with this fantastic quote from a CPython core developer, which was posted in the discussion about this exact attack. This isn't really a failure of Python's dictionary. This is a fundamental trade-off in computer science. Hash tables trade a guaranteed worst-case performance for an absolutely spectacular average-case performance. And understanding that trade-off and knowing when it really matters is what separates the good programmers from the great ones.